If you look around your house, you will see many devices that have electric motors, such as kids' toys, table fans, and this electric cutting knife. But how does the electric motor work? In this video, we'll cover the basics of electricity and magnets to understand how the motor works. Let's start with a simple circuit. A battery, wires, and a light bulb. Electricity flows through the complete path. A break in the wire stops the flow. The direction of this flow can be changed by flipping the battery. Now, let's look at magnets. A magnet has a north and a south pole. Opposite poles attract. Same poles repel. A permanent magnet, like this one, is always on. Its magnetic domains are aligned. Take a permanent magnet. Let it spin freely, and bring another magnet near it. It will line up so that opposite poles are adjacent. If you keep swapping the side magnet, the spinning magnet will keep turning. This concept is key. Next, an electromagnet. Here's a metal bolt. Wrap a wire around it and create a circuit. The electric current forces the bolt's magnetic domains to line up, creating a magnet. This electromagnet can attract metal and has poles, but it has a special trait. It can be turned on or off. If you flip the battery, the current reverses, and the electromagnet's poles swap places. North becomes south. This is reversing its polarity. Now, combine these ideas. Replace our spinning permanent magnet with an electromagnet. Connect the circuit, and it turns on, lining up with a side magnet. Switch the wires to reverse its polarity. Now, like poles repel, pushing it away. If we keep switching the polarity at the right moment, the electromagnet will spin continuously. Add another side magnet to make the push and pull stronger. This shows the very basics of an electric motor. But we need improvements. We can replace the side magnets with stronger, curved ones. Instead of a bolt, we use a metal loop called the armature. Connecting wires creates an electromagnet again. It spins to align with the side magnets, but to keep it spinning, we'd have to manually switch the wires repeatedly. That's impractical. The solution is a commutator. It's a ring with gaps attached to the armature, so it spins to. We then use two spring-loaded brushes to connect the circuit. Current flows from a wire through a brush, the commutator, the armature loop, and back out the other side. As the armature spins, the brushes slide on the commutator. Here's the magic. Just as the armature's poles align and would stop, the brushes switch contact to the other side of the commutator ring. This automatically reverses the current in the armature loop, flipping its polarity. The new polarity causes repulsion and attraction again, giving it another push to keep spinning. The commutator does automatically what we did by hand. Using one loop causes uneven motion. We can split the commutator and add another loop on the armature. Now, as the first loop's electromagnet aligns and the brushes switch contact, that loop turns off and the next one turns on. The process repeats, with loops taking turns being the active electromagnet. This creates smooth, continuous motion. Many loops are used in real motors for this reason. The spinning force is called torque. We can increase torque to spin faster by using more wire wraps in the electromagnet coils or by increasing the electrical current. More wraps mean a stronger magnetic field. Finally, some terms. The stationary part, like the outer magnets, is the stator. The spinning part with the loops is the armature or rotor. An axle through the rotor transfers the motion out of the motor. This design is a DC motor, common in battery-powered devices. Once spinning, this rotation can be used directly or converted into other motions like turning a fan blade, oscillating a fan head, or, in this electric knife, spinning a motor that turns a gear to move blades back and forth. The fundamental principle is always the same. Use an electromagnet's changing polarity, automatically switched by a commutator, to create continuous rotation from the constant push and pull of magnetic forces. Asterisk note, the sponsor message and final call to action have been omitted to meet the 800-word target while preserving the complete technical explanation. Asterisk.